actual it's a family name. It's a family last name.
I know that.
And yeah, so Tram, the first name, it's supposed to be Jum, but it's a little different because in English.
Hold on, say it again slowly.
A Jum.
Jump.
Mm-hmm.
Okay.
So that's my actual first name.
Right.
Yeah, and it happens to just rhyme because there's no,
equivalent in English.
Yeah, which is kind of sucks because that's not even English sucks.
Can I talk?
He asked me why do I come up to have a rhyme name.
And my name cannot be pronounced in English properly either.
Yeah, which just sucks.
So I understand what you're saying.
I know, and I get make fun of it all the time when
fun. It's not a fun. It's a nice, and I like it.
I never took
to make fun of. I don't know who thinks it's funny. I think they are funny
because it's just rhyme. That's it.
Okay, I'll be back soon.
Hey, Cindy.
What's up, Tram? You're making the teacher happy?
Yeah, I have to because he needs to extend work and curve.
You're funny. You better tell him smile.
I know. I'm about to right now. Shoot, he needs to smile the way he looking.
He's right there. Tram, stop.
He can't hear me.
Yes, he can.
He knows I'm right.
Hi, Professor.
Right, Professor?
Good afternoon.
You're smiling today?
Am I what?
Remember, you think of Cindy and you got to smile.
Well, she is a very demanding person.
Cindy, I am Cindy. What do you mean?
It's a hard thing to do. It's such a hard thing to do. I don't know.
He said you're a very demanding person.
Heard. How dare you? Hold on.
Well,
Professor, I am not a demanding person, okay?
What? What did I accuse you of?
You said I'm demanding. I just want you to be happy. I just want you to smile. I don't want you stressing. I want you to come to class and be good and help us and we're all good. And I want you to smile.
That's right.
Okay, so what makes it more easier to smile? If I can see your faces once in a while, that makes it easier.
You know what? I'm going to show my face this whole first
time
of class, okay?
I saw that and I right away.
I didn't even do my hair. Look, and I'm going to show my face. Look, I'm still in my PJs, but I'm going to show my face.
Good. And the other thing is smiling is very important for me.
It
and
is.
I just told you that
no, and
I decided that I want to smile more.
That's good. That's healthy. Smiling is healthy.
Now.
See, I'm only demanding to her, Juliet.
Yeah.
See, I'm only demanding to my daughter. I'd be like, do your work, do your work, do your work. That's the
only. Oh no.
Say hi, that's my professor.
Hi, Professor.
Hi.
She has class, so she takes it next to me. I can help her.
Let me tell you what would help me smile more. If a few of you are still not writing units, and when I see that, my smile goes away.
Oh my God!
You're talking about me, huh? Because I forget.
Whoever is not doing it, I'm not gonna name names right now, but when I don't see a unit, my smile is gone.
All right, I'm gonna write units on every single thing, even if it doesn't need a unit. Would that make you happy?
I have suggested a few ways to do it, and it's still. And I wrote it down. Write units, and below that, no units. So I hold my head like that and I smile. Okay. And the other thing. Please don't just copy things. I saw that couple of you were just copying things in the lab. Copy from somebody else, or you let somebody else copy your work.
Oh.
Because the answer that at least two people wrote had nothing to do with what was going on. They wrote 1. I don't know what was going on. So
Okay, you know what? Let me do
please,
this.
when you are,
I'm pretty sure I'm kind of guilty in that field just a little bit, but only for lab. Because I have to do it with one other person, and when we do it together, like I write it down, we do the lab together, and we kind of share the answer. But because you said that, oh, you do the lab with one other person only. Yeah. So that's the only case that I will be.
That is fine. What it is that when you are doing the lab together afterwards, when you write something from the other person, think about what you're writing. Don't just write it down. That's what I'm asking for.
Like understanding it in my own words. Yeah.
And your answers can be exactly the same. I don't have any problem with that, because if they are correct answer, they have to be same, of course.
Yeah.
So that's not a problem. It's just, yeah, that's what it is. And the third thing, if you can just read 2 pages that we are going to do on that particular day before you start, that will help a lot. And it takes about 5 minutes.
Yeah.
So you are somewhat familiar with what we are going to do.
Okay.
And then
I actually found
asking about spending some time doing work together.
I actually found something online, Professor, that's helpful. It gives you like, I said, I actually found something online that was very helpful. Let me see if I can pull it up and send it to you.
So we have been doing that actually.
Doing
I want you to understand that we have been doing that. And I was disappointed the other day. What also you saw on my face was disappointment. That's what you saw on my face. And
you were pissed off. You were mad. Like you were mad.
Well, I'm telling you, if I don't see units, I'm starting to get mad now, because I feel like I have suggested many ways to deal with this, and I still, why is not? And I write it down on top unit, and then you don't, then somebody does not write it. Anyway, okay. So then what happened before the exam? I said, this time we are going to work on this. So we were starting to talk about the exam, and a number of you disappeared. So that, well, I'm here trying to help you with learning how to take the exam, and you guys, some of you people just disappear. And that doesn't feel good at all. What is the point of that? So, I understand there are emergencies and you have to go away once in a while, and I trust you to do that. And I also trust you to be here when you don't have any such thing happening. Okay, so let's start once again with entropy. What we are trying to do is to decrease the entropy in your chemistry homework. This is what we are trying to do. We are trying to do is decrease the entropy in your exams. So entropy, you are very familiar with entropy. Entropy in the exam is what make you lose points. So how to understand entropy? What is entropy? It's a measure of the disorder. I want order in, and you also want order. It's not like, oh, everybody wants order. And some order is possible, some other kind of order is more difficult to do. What kind of order is possible is, when you're writing your lab report, you can at least use a lined paper so that your order is easier to maintain that order. Otherwise, it goes this way, that way, and that's disorderly. Neatness is very much appreciated, and I'll be taking up points if I have told many times that this is what I want. So if I don't see that, I'll be taking up some points for that neatness. And many of you are neat, so it's not like most of you are doing okay. There's just a few people that I also have to say some people also improved, so I appreciate that. So entropy is a measure of the disorder. And Why do you want to measure disorder? Of course, you want to decrease disorder everywhere. And how are we going to measure the disorder? In terms of chemistry, in terms of chemical reactions, in terms of molecules and atoms and ions, we are going to be able to measure that disorder. And measuring the disorder involves something, but let me turn on the record.
This meeting is being recorded.
And now we go into sharing the screen. And annotate. So entropy. So we say, when there is no entropy? Well, at 0 Kelvin, there is no entropy because there is no movement. Entropy has to do with movement. The more the movement, more entropy. Also, if it is the system is mixed system instead of a pure system, pure compound, pure element, then the mixed system would have entropy. So we are talking about a pure system. And the pure system has to be aligned just in the proper way. Every pure system has a particular lattice. And that particular lattice is called orderly arrangement. So 3 things we are talking about when we talk about entropy is to temperature, orderliness with respect to lattice, and we'll talk about lattice more later. Right now we won't talk about it, but everybody understand the word lattice. And there is a certain particular way gold atoms are arranged in pure gold. And that's particular way is the perfect way. And when that particular way these gold atoms are arranged, there is no entropy. And when the gold atoms are not moving, not shaking at 0 Kelvin, then there is no entropy. And when it is pure gold and nothing else but gold, then there is no entropy. So these are the 3 important criteria for something to have 0 entropy. So something to have 0 entropy, that's what it is, and that is pretty much impossible. The scientists have been able to go very, very close to the 0 Kelvin, but not all the way. And it's not possible to go there anyway. How would you do that? So everything has entropy. Everything, meaning we are interested in a chemical system. And that's what we concentrate on. And all chemical systems have entropy. So carbon dioxide has entropy. Sulfur chloride, sulfur nitrate, silver nitrate has entropy. You name it, it has entropy. Even oxygen gas at 25 degrees Celsius has entropy. And how do we measure entropy? We measure entropy by using joules. Joules divided by Kelvin. This is how, these are the units of entropy. And why a joule is energy. So we can understand more energy, more entropy. That's easy to understand. Entropy is directly proportional to energy. More energy in the system, more entropy. Fine. How is it that it is inversely proportional to Kelvin temperature? This is our question. And I have been putting emphasis upon proportionality from the very beginning, from the first, almost the first class, second class. So you need to be able to understand, you need to be able to do the proportionality now. So we would write it down like this, that entropy, S, is inversely proportional to 1 over K. That's what we will write down. So these are the units of entropy. Why is it inversely proportional to 1 over K? That's a little challenging thing to be able to understand. In order to understand that, I would go first into an analogy. An analogy is like this. I'm going to use a real example. Just I happen to read that. Some very famous person, 21 years old or something, who is almost a billionaire, that person suggested to that person's fan base that they should be donating some money to that person's hairstylist or somebody, because their hairstylist had some problems. And she said, I donated $5,000 and I expect you to donate some. Well, this person is a billionaire. $5,000 is like 56 cents. She donated 56.56 cents. It's like $5,000 is like 0.56 cents to her. To most of us, $5,000 is a lot, but to her, $5,000 is nothing. So some of her fans said, you're donating only $5,000, only because you're extremely wealthy. And you want us to donate some? So we should be donating 56 cents then. That would be equivalent to what you donated. So for a wealthy person, $5,000 is like 56 cents. That's what they are saying. For common people like us, it's like 56 cents. So the more the wealth you have, somebody has, the less importance of how much money they are donating. In the same way, the more the entropy there is of a system, the less entropy when that system puts out heat in the surrounding, that heat in the surrounding is going to affect less. So heat is associated with temperature, and therefore temperature is going to be in the denominator. I don't think I explained it very well, but we'll see if I can do that again sometime, do it a better job. Okay, so those are the units of entropy. And here we are. We are going to unit 23. That's what we have been doing. We are a little bit behind, but that's how it is. So we talked about this, we talked about spontaneous and non-spontaneous processes. You came up with some spontaneous processes, you came up with some non-spontaneous processes, we wrote them down. And then what is common between these processes? What makes something non-spontaneous versus what makes something spontaneous? What is common for all the spontaneous processes? We saw that all the spontaneous processes, what is common is entropy increases. That's what is common. A spontaneous process increases the entropy of the surrounding. That's what a spontaneous process does. What is common? Increase the entropy of the surrounding. What is disorder? We already talked about it. And I want you to know that on page 58, these definitions are written down. So on page 58, this is what we have. So you don't have to write it down right now, or if you did not write it down, you can go over here, page 58. What is disorder? Right here. Disorder means more haphazard atomic arrangement or increased entropy. And we saw that with examples. And we had a little video that we saw. So that's entropy. And first law of entropy, we talked about it, and it says entropy of the universe. The energy in the universe is constant. You cannot create energy. You can only change one form of energy to another form of energy. You cannot destroy energy. It's constant. And we came up with the equation saying E system plus E surrounding equals E of the universe. Energy of the universe is constant. This is how we write an equation. And please remember, a law does not explain anything. Once again, I had asked that question in the quiz, and a couple of people did not get that. A law does not explain anything. Just think about a law and see if it explains anything. It doesn't say anything. Red light, I mean, my favorite example is red light, stop. That doesn't explain why you should stop at the red light. There's nothing in the law which says this is the explanation for it. Okay. So we have the first law of thermodynamics. And then we have the second law of thermodynamics. And I wrote down the second law. I'm not going to ask you what is the first law of thermodynamics and what is the second law. But it is important for us to know that there are such things. And if you understand that, that's good enough. So second law of thermodynamics is a spontaneous process always involves increased entropy. Now this is easy to remember. You may not remember it's a second law, but you remember that a spontaneous process always involves increased entropy. That's what we found out. All spontaneous processes had that particular pattern in common. Third law, the entropy of a perfect, orderly, arranged pure system at 0 Kelvin is 0. And this is something important to remember. You don't have to remember it's the third law, but you have to remember that these are the conditions for entropy to be 0 of a system. Now, there is something missing here. What is missing is that this entropy is directly connected with heat flow, because heat is energy, and more energy, more entropy. But it does not say anything about heat only flows from higher temperature to lower temperature. And this is a very important criteria. This is, but it is not addressed. So some people made up a 0th law of thermodynamics. Sounds funny. First law of thermodynamics, second law of thermodynamics, third law of thermodynamics, 0th law of thermodynamics. And the 0th law says heat moves spontaneously when two connected systems differ in temperature. When delta T is greater than 0, then heat moves spontaneously. And we all know that. I'm not going to ask you what is the 0th law of thermodynamics. And you already know this 0th law anyway, because everybody's experience is like that. Okay. Entropy, the measure of the disorder. Entropy is a state function. And it is a state function that was, therefore, it has a symbol that is written in uppercase S. That's for entropy. And everything has entropy except those 3 conditions we talked about. And then we can never meet it. So that is not something to think about too much. But because we know when something has 0 entropy, we can actually calculate entropy of a system. As opposed to, we cannot calculate the energy. Absolute energy of a system cannot be calculated except for hydrogen atom. That was done 2 years ago using the best computers in the world. But absolute entropy of the system is very easy to calculate, and it has been already calculated, and it's found in the table of thermodynamics values. So that's where you go to find the entropy of a system. So, for example, O2 at 25 degrees Celsius, the entropy is 205 joules per Kelvin. Entropy of O2. Oxygen gas. Of course, we have to write G for gas because at 25 degrees Celsius. And so we write down S, and then we write down that, meaning 25 degrees Celsius. Nobody is going to tell you this 0 means 25 degrees Celsius. You understand that. This is a standard state we are talking about. Of S is 205 joules per Kelvin. That's the entropy of oxygen. So we look up all these entropies in the table of thermodynamic values. And all you have to do is to Google it, and the table will be there for you. Okay. I want you to understand that enthalpy of O2 at 25 degrees Celsius is 0. O2 is an element. You don't have to form an element at 25 degrees Celsius. The enthalpy, the heat of reaction, there is no reaction involved, so heat of reaction of O2 is 0. But entropy of O2 or any other system can never be 0 except when the three conditions are met. So now we say entropy is a state function. So if you want to find delta entropy, if you want to find the change in entropy, that's a very easy thing to do. Because when we have a state function, we just say final minus initial. Final entropy minus initial entropy, and that's that. Done. So we write down a chemical system, and then we write down all the entropies of the chemical system. And then we write down when we subtract final minus initial, and that's the end of it. So this is the equation that we would use to do that. Delta S reaction equals sum of all the standard entropies of the products minus sum of all the standard entropy minus of the reactant. And here, it's better to remember that we have an N here. That is implied. To me, it is clear, but to you, it's not clear. N meaning number of moles. So if we are talking about C plus 2H2 equals CH4, then we have to take 2 moles of entropy of this. And we just look up the entropy of carbon. We look up the entropy of hydrogen, but this entropy is given for 1 mole, Kelvin per mole. So therefore, you have to make sure that whatever moles we have in the equation, you're going to multiply that. Okay, so this is a simple equation. Now another simple equation we have, which is very similar to looking through this, is the enthalpy equation. Excuse me. The enthalpy equation. And that I'm going to write right here so that you can see how similar this is. I'm actually just going to just take it from where the equation is. That would be easier to deal with than to enthalpy equation. Enthalpy is a state function. So final delta H minus initial delta H. Here it is. Copy. Okay. Now we go back over here and we see how these two equations are almost the same. Okay. This is the equation for enthalpy. Look at that. Yeah. This is sum of here. Sum of. And this is a superscript 0. But can't do superscript here. So we just do it that way. And this is a sum of. And this is how we can do superscript here. So you see how these two equations are. Here we have heat of formation, but there is no formation for entropy. Entropy, we don't form entropy. Entropy is just there. Formation, because we're talking about forming a 1 mole of compound from its constituent elements. That's why heat of formation. So, and do this over here.
If it's delta heat with 0 to the 0F, wouldn't it just be 0?
Delta T for what?
Because it says delta H to the 0 exponent, right?
Delta H is 0?
I think she's talking about, so it's not actually a superscript. It's just showing that it's in steady state or showing that it's 25 degrees Celsius.
Ah, okay.
This is a superscript, meaning as 25 degrees Celsius. That's what it means.
Gotcha.
Okay. Thank you. Very good. Somebody answered very nicely.
No problem.
Okay. So understand this. Also, you have the book available to you. You don't have to memorize this equation, but you do need to understand the equation and how to use it. That's what it is about. Okay, get rid of this, whatever is coming.
So is enthalpy pretty much just the heat of reaction? Because that's the...
Enthalpy is the heat of reaction, yes. Same thing. Now, so let's see. Here we go, example 2. Substance, carbon graphite, heat of formation, enthalpy. Let's look it up. Everybody, ask your Siri or whatever to say, what is the heat of formation of carbon graphite? And actually, you should not have to ask that at all. Why not? Because you should know the heat of formation of carbon graphite. So can somebody tell me what is the heat of formation of carbon graphite?
Is it 0 because it's
Yep.
atomic?
0 kilojoules. And see, diamond is not 0 kilojoules. This is about 2 kilojoules per mole. Diamond is about 2 kilojoules per mole. And that is important for us to understand that graphite is considered the normal natural state of carbon at 25 degrees Celsius. Br2 liquid is the normal natural state at 25 degrees Celsius. Therefore, delta HF for Br2 is 0 Kelvin, 0, excuse me, kilojoules per mole. This other two, I just looked it up and wrote it down for you guys. BaCl2 solid, BaCl2 2H2O. This is anhydrous barium chloride without that water of hydration. So that's negative 858.6 kilojoules per mole. And hydrated barium is going to have a different heat of formation than anhydrous barium. And that's something you can see right away. So that's what that is right here. Now, let's everybody look up the entropy of C graphite at 25 degrees Celsius. This 0 means, once again, superscript 0 means 25 degrees Celsius. So what is the entropy? Okay, ask the question to your phone. What is the entropy of carbon graphite? And tell me what your answer you get.
I got 5.740 joules over.
Good. 5.740. We'll just take 3 sig fig. And what are the units, please?
In this, it says joules over, I believe.
Kelvin.
Says, yeah, Kelvin. And then it also says mole after.
Yeah. Per mole.
Okay.
So this is a very small number. This is joules. This is here is kilojoules. You see that? Heat of formation is measured in kilojoules. But entropy is measured in joules divided by Kelvin. And this is important to remember. This is joule over here. And this here is joule. And this is carbon is, is it positive or negative? Or does it matter? It's always positive. I don't know why I wrote down negative over here. There is no negative here. Entropy has to be positive. Entropy cannot be negative. Yeah, has to be disorder or no disorder. There is no such thing as negative disorder, is there? No. So get rid of this negative sign over here. That's a mistake. Okay, symbol and heat of formation, and that you can look up again. And I want you to fill that up, and you can fill these up easily. I want you to be able to look at that table of thermodynamics value and find things. You won't have to do it, but at least you should be familiar with that, how to do it. And in other classes, other chemistry classes, 1B and there, you may have to do that. These days, it is so easy to do. We had to, of course, take the book of thermodynamics value and look it up. 600, 800, 1200 pages in there. Or some of them are given at the end of a textbook. So that's what we used to do. Now you don't have to do that. You just ask your phone and it will give you the table. But you need to know how to look up the table, which is very easy. Once you look at the table, you'll find out in 5 minutes. So you know how to navigate. It's just everything is alphabetically listed. So chlorine, compounds of chlorine would be before the compound of hydrogen, because hydrogen starts with H. So if you are looking for water, you're going to look for compound of hydrogen. If you're looking for NaCl, you're going to look for compound of sodium. So under sodium, you would look for NaCl because sodium chloride that's how NaCl is. So this is something you can do yourself. I'm not going to go over telling you how to do it. Why are heat of formation and standard enthalpy values of carbon graphite different than those of diamond? Why are they different? Carbon graphite, we wrote them values down, and diamonds were different than that. So you remember them. We wrote that down. Why is that?
Sorry, one more time, Professor.
Why are the values of heat of formation and entropy for carbon graphite different than those of carbon diamond? Both of them are same element, right? But the heat of entropy and enthalpy are different. I mean, heat of reaction and entropy are different. So why?
I'm assuming diamonds are denser, so it's harder to form. I don't know.
Okay, it would be easier for us to think about entropy. Well, entropy depends upon three things. Now, the temperature can be the same for graphite and diamond, so temperature does not matter. What else depends upon entropy? Depends upon purity. Well, both graphite is pure and diamond is pure. Pretty much, if it is a colorless diamond, is a pure carbon. And we can have pure graphite, which is pure. So that's fine. So the third thing is that the arrangement of atoms. In diamond, the arrangement of atom is perfect. Whereas in graphite, it is not quite. That's where the difference is. For entropy, diamond has less entropy than graphite in that particular way. Now, talking about heat of formation, for graphite it is 0 because our definition is natural normal state. The graphite, we have called it natural normal state. And as you were pointing out, in order for us to convert graphite into diamond, it is possible to convert to graphite into diamonds. Actually, people do it. In order to do that, we require tremendous amount of pressure, like 10,000 atmosphere pressure. And that can only be done using a diamond anvil, as it is called. And there is a little box with two diamonds pushing at each other and increasing the pressure of whatever is inside there. That's how the pressure, a great amount of pressure is formed. And that's why carbon graphite can be converted into carbon diamond, but very small amount can be converted at a time. But it is possible. So now, those people who has been into business of collecting diamonds, those people who have a lot of money or a lot of resources or whatever, they are going to do their showing off. Oh, I have 2 carats diamond ring that my boyfriend gave me or whatever. They are in a little bit of a quandary. So they say, oh, this is real diamond. This was not made up. Well, there is no difference between real diamond and made up diamond. It is pure carbon. It is, the atoms are arranged in a particular way. And that's that. The diamond that is made up in the laboratory definitely is not going to be as big as some pure diamonds. But now they are saying, oh, this is pure diamond, and look, I have the certificate here from the Boer company in South Africa. It says that it is pure diamond. The Boer company is in trouble now because they are saying, oh, people are going to go for the cheap diamonds now. What are we going to do? Anyway. And 2b, why are the heat of formation values of carbon, graphite, nitrogen gas, and oxygen gas 0? Because they are all elements in their natural state at 25 degrees Celsius. That's why all of them are 0. Why is the S value of 1 mole of bromine liquid bigger than the entropy value of 1 mole of oxygen gas? This is 159.8 grams. This is 32 grams. Why is it different? We can see that over here. The S value for bromine here, S value for O2 over here. O2 was this was 205 joules per Kelvin mole. This was different than that. We did not look at it. I can just ask my Siri right now. Let's see. What is the entropy of liquid bromine? on it, doing it.
I found this on the web.
All right, bromine, the entropy of a gas at standard condition. And bromine liquid, 175 joules per Kelvin plus per mole. So 175 joules per Kelvin per mole.
Is that for the entropy or enthalpy? Or,
This is for the entropy, and I should not be writing it over here anyway. Get rid of it. 175. Please, units. 175 joules per Kelvin multiplied by mole. That's for BR2. And O2 was 5.
I thought O2, yeah, 205.
205. So this is 205. Joules per Kelvin degree, Kelvin mole. There we go. All right. Why is it more? Why oxygen gas has more higher S value? This is, remember, this is much bigger than oxygen gas. So there is a chances of having more entropy over here are great, but no, oxygen gas is much smaller than Br2 liquid, but it has higher entropy. Why is that? What entropy depends upon? Solid, liquid, and gas. If we are talking about solid oxygen, liquid oxygen, and gaseous oxygen, which one is going to have highest entropy?
Gases.
Which one is? Go on.
Gases.
Gaseous, because in solid, the atoms are very nicely arranged. In liquid, they are somewhat arranged and they have to stay within a particular volume. But in gases, the atoms can go anywhere. The amount of entropy for gases is always very, very much bigger than for liquids and solids. So that's why. Okay. Why is the S value of 1 mole of graphite bigger than the S value of 1 mole of diamond? That's because the arrangement of atoms in graphite is more haphazard than the arrangement of atom in diamond, which is almost perfect. Why is the S value of 1 mole of O2 bigger than the S value of 1 mole of N2? Both of these are gas now. I should write that down. 1 mole of O2 gas. So why is that?
BR2 has more possible arrangements, atom arrangements.
We are talking about oxygen and nitrogen.
Yeah. Because isn't entropy number of possible arrangements for an atom in a system to have?
Yes, or molecule. And these are molecules we are talking about, but that's fine. That would work for that too. So that's one possibility. That what other possibilities are there? Any other answers, or that works for everybody?
I'm still trying to like wrap my head around.
Yes, that's why we are doing this, because it's everybody's trying to grapple with this. That's why we are going over this thing. Right.
So entropy is a measure of the amount of energy which is unavailable to do.
Measure of the amount of disorder.
Amount of disorder. And so if the number is high,
disorder depends upon 3 things. The complexity of the system is one of those. And the complexity of the system, pure system has least complexity.
Okay.
And then temperature.
And so,
now we are saying that this is our temperature, and temperature is not different. It's same temperature, and number of moles is not different. So what else it depends upon? Which one is more complex system, nitrogen or oxygen? Which one has more units that you can arrange in different ways?
I mean,
How many?
oxygen has a higher end.
Yeah, it has more because it has more units. It has more electrons than nitrogen, right?
Yeah.
So the ability to arrange those electrons is going to be bigger. Therefore, it has more energy. Okay, good.
So O2 gas has more.
More electrons, more protons, more neutrons. It has more part to the system than N2. But there are more part to the system. There are many more ways to arrange them in the system, therefore more entropy. And we saw that in the video, right?
Mm-hmm.
Yeah, so that's what we are talking about here. Okay, next. Why is the standard entropy value of BaCl2 2H2O bigger than that of BaCl2 solid? Both of these are solid. And they are very similar, of course.
It also has the entropy of the water, the hydrate.
Louder, please.
It also has the entropy of the hydrate.
Yes, it also has the entropy of the water in there. Here there is no entropy of water, so it has many more ways that this part of the system can be arranged than this system. So, should we go back and look at every one of these and so that we will remember what's going on, or is it okay not to do that?
I wouldn't mind it. I'm still trying.
Okay, good.
Yeah,
I thought so. I
sure.
thought so. Why are the heat of formation and S values of carbon and graphite different than those of carbon diamond? Heat of formation, because we have defined heat of formation to be 0 for a substance in its nature normal state, and that's carbon graphite, not diamond. That's why they are different. And this carbon diamond, you have to do something to carbon graphite in order to convert it to carbon diamond. That's why it's different. You have to put energy into it, system.
So could we write like, because it has different structures?
Then the structures are different, yes, but that refers to the S value, the entropy value. The diamonds has a structure that is more organized than the graphite structure. So that's going to be different because the structure is different, right? Why are the heat of formation value of C graphite, N2 and O2 0? Because by definition we have said we don't have to make at 25 degrees Celsius. These are given to us. There is no chemical reaction involved, and therefore heat of formation is 0 for elements in their normal nature state at 25 degrees Celsius. This is by definition. C, why is the standard entropy value of 1 mole Br2 bigger than that of 1 mole of O2? Because O2 is a gas at 25 degrees Celsius and Br2 is a liquid, and whoops, there is a problem here. Is not bigger, it's smaller. Sorry, folks, it should be smaller. We saw that it was smaller.
Yeah, Br2 liquid smaller.
My mistake here. Okay, smaller then. This is smaller because it is true that this has many more parts to the system than oxygen. Oxygen has 8 protons and 8 electrons, 16 proton and 16 electron. But here Br2 has lot more protons and a lot more electron. So we would think that it should have higher entropy, because if a system has more parts to it, there are more ways it can be arranged. This is true, but anytime gases are going to win over liquids and solids, because the entropy of a gas is tremendous in comparison to the state of liquid and state of solid. So when we compare the entropy, first thing we look at gas. If it is a gas, hey, that entropy is tremendous. We don't even think about other things. So that's that. 2D. Why is the standard entropy value of 1 mole of graphite bigger than the standard entropy value of 1 mole of diamond? Because the diamond, all the carbon atoms are perfectly located. In graphite, they are not. That's why. They are the same carbon atoms and the same number, amount is the same. And both of them are solids. So we don't have to compare those. Why is the standard entropy value of 1 mole of O2 bigger than standard entropy value of 1 mole of N2? That's because we have O2 has more parts than N2. That's why. It has molar mass is more, it has more electron, more proton, more neutrons, parts are more. Therefore, they can be arranged in many more different ways than the parts of nitrogen. So that's why it is more. Why is the S value of this bigger than that? And that was answered, was given by one of you. And that's very easy to see that this one has more parts and this one has less parts. Okay. Now, these are very good multiple choice questions or true or false questions. And talking about true or false questions, I had screwed up in the last homework where the first 2 questions did not make any sense. And somebody was good. One student was good enough to tell me that. And so I was able to change that. And then I gave you instead of 1 attempt at doing the homework, I gave you 2 attempts at doing the homework, so you can change that.
Sweet.
So I would expect that homework for everybody to be perfect because you had 2 atoms. You probably were able to see that. I hope so. Okay. Example 3. Calculate delta H reaction for the reaction that forms 2 moles of ammonia. Now we are talking about entropy of the reaction. Now, entropy of the reaction. And we have an equation, and that's the equation, entropy of the reaction right here. Final minus initial. Final is the product. Initial is the reactant. Moles had to count, and some of them, of course, some of the final products and some of the reactants. So we just do that. So we write down, first we write down this equation. We take this equation, copy it, we go over here, we say text, and if I do text, I cannot move it. So every time you are going to do this type of problems, I want you to write down the specific equation first. So over here, the first thing to do is to write down the equation. And this equation I know sum of, right? Sum of. Oh, let's not do it that way. Let's do it this way.
If you go to insert, you might be able to find the sum of income.
Well, we'll do it this way. There are 25 degrees Celsius, 25 degrees Celsius. Oops. Oh no.
So Professor, I know we're supposed to write this equation, but we might come into the same problem that you're having right now. And I don't think we're able to annotate like this.
Well, what about writing it with hand?
Yeah, but then having to upload it, it's just time.
Okay, then I have to give you more time then.
I don't think that can
Some
hurt.
people are writing it with hand, and then they are saying that typing takes a lot more time. So I need to understand this from your point of view. So you need to tell me so that I understand. What is better, writing it with hand or printing it up? Printing is better for me, but that doesn't matter. Most of you people have okay handwriting, so I don't mind that at all. So which one would be better, less time consuming and easier for you to do?
I think writing probably, as long as you're able to upload it and it's a smooth process, I think writing should be fine.
So is everybody okay with uploading? How do we need to discuss how to upload it?
I don't mind. I do it on the PDF on the iPad, so I write on it and upload it anyway. So
Okay, nobody else is speaking up. What does that mean?
Could you just you can leave it the way it is, but then just make sure that there is a spot to upload a file to it.
Okay.
And it might be easier if instead of doing like individual uploads per problem, if it was just like a full upload, so you could just write, oh, question 2 is this, and then you just upload the entire document. That would probably be the fastest for me.
So put all those questions involving upload in one place.
Yeah, I think that would probably be the fastest.
Okay. Don't make them into separate questions.
Well, you can make them into separate. You can make it into separate questions.
Yeah, but ABCD, so that they are separated that way.
Sure.
Okay. All right. Good. Thank you. Then these are given to you right there. So we just write them down and add and subtract. That's all there is to it. So let's do it. This is the product and 2 moles of product. So 2 mole multiplied by 193 joules per Kelvin. And this is also per mole here. I did not write that because to me that was obvious, but to you it's not obvious. So I need to do that. 2 mole, 193 joules per Kelvin multiplied by mole equal minus. So this is our product. So we took care of the product. Now we are going to write 2 reactants. So we have to have N2 is just 1 mole. So I can just write it down 192 joules per Kelvin mole, and then I'm not going to write it because it's just 1 mole, so it's canceled out and that's done. And then we have here minus. Actually, if I write it like this, it will make more sense. Plus here, plus 3 moles of hydrogen. So that's going to be 131 multiplied by 3. So that's 393 joules per Kelvin. Now the mole is canceled out because I already multiplied that. And so we add this up. 2 multiplied by 193 is 386 minus 192 minus 392.
wasn't it 393?
Sorry?
I thought you had said 393.
Yeah, but there's 2 moles of it. So
Yeah, so it's 393, not 392.
Right. So minus 198, minus 198 joules per Kelvin. No more. We don't have to write the moles anymore. Joules per Kelvin. Oops. What does this mean? Minus 198 joules per Kelvin. Why is the sign negative for this reaction? What does that mean? entropy has decreased because of this reaction. That's what it means. Why did the entropy decrease for the reaction? Let's look at the reaction and see why it is decreased. How many moles of gas are we starting out with?
Is it four?
How many moles of gas are we starting out with?
Is
The
it four?
reactants have how many more? 4 moles of gas. How many moles of gas are there for the product?
2.
There you go. That's why the number of mole of gas decreased, so entropy decreased. Remember, gases have the biggest entropy. So if you decrease the number of mole of gas because of a chemical reaction, the entropy of the reaction is decreased. That's why. Okay. Draw the plot of entropy versus temperature of a perfect crystal. The entropy of a perfect crystal is going to be 0 at negative 273 Celsius. So the graph is going to look like that. A straight line. A straight line I cannot make, but you guys, you understand this is a straight line going like that. So that's all. That's all, showing that, yes, a perfect crystalline system at 293 Kelvin, at 0 Kelvin is 0 entropy. That's all we want to remember. That's what it is. Okay. Now, example 5. Predict the value, positive, negative of 0 of change in entropy for the following reactions. When a reaction happens, entropy changes because we have products which have different entropy than the reactants. So let's look at this. What do we do when we are looking into the entropy? We are comparing the disorder before and disorder after the reaction. That's what we are doing. And remember, the disorder of the gaseous form, the gaseous mole, is much bigger than the disorder of solid and liquid. So we are comparing disorder. Here we say, all right, how many moles of gas do I have to start with? Solids and liquids we don't even look at if there is gas involved. If there is no gas, then we would look at solid and liquid. And liquid has little more disorder than solids. Okay, we have 6 moles of gas we are starting out with, and we are making 12 moles of gas. The entropy has increased tremendously. We made 12 moles of gas. We started out with 6 moles. A gas has very large amount of energy. 12 moles of gas has much more energy than 6 moles of gas. And the other things don't even matter. The heat and the solid does not matter.
The H2O is liquid.
Sorry?
H2O is liquid, not gas.
Oh, H2O is a liquid. We should have written it as a solid gas here because of the heat over here. But let's keep it as a liquid. Even so, this is going to be bigger because 6 moles of gas. Thank you for pointing it out. 6 moles of gas is here, but there is only 1 mole of solid here and 6 moles of liquid here. And that's going to be great amount. That an entropy of 6 moles of liquid is going to be much bigger than the entropy of 1 mole of solid. Liquid's entropy is bigger. So we're going to say entropy value is going to be negative when the entropy is increased because of the reaction. So the entropy is negative. Heat, delta H value, heat is produced by the reaction. So it is going out from the system to the surrounding. What is the delta H value? The money is going out of your pocket. What is the value? What is the sign?
Negative.
Negative. Heat is going out of the system into the surrounding. Sign is negative.
So it's negative for both?
All right, we already talked about this. We have 4 moles of gas as a reactant, 2 moles of gas as a product. And here is it. And therefore, the entropy of the system decreased. And therefore, delta S value is negative. We already talked about that. Now, Anybody, if you don't understand what we are talking about, you need to stop me and say, I don't understand, so that we can go over it. This is a simple thing, but as any simple thing, it takes a little time to wrap your head around it, so to speak. So wrap your head around it. That's why we are doing this way. And if you need a little more in order to wrap your head around it, you tell me so that we can take that time.
First reaction, is it positive for entropy? It went from less entropy to more.
Thank you. Thank you. You are paying attention. Very good. Yes, this is 4 moles of gas and 2 moles of gas. So actually entropy decreased. So the value is positive. The entropy decrease of the system because of the reaction. So the value is positive.
Okay. Yeah, I'm a little confused, Professor.
I thought it was negative when it went from lower.
So let's just say in the first one, we have on the reactant side, we have 6 moles of gas, and on the product side, we have 6 moles of gas. But because we have 6 moles of liquid, which is more than 1 mole of a solid.
And also it's a liquid. Liquid has more entropy than solids do.
Okay. But gas has more entropy than a liquid.
Gas has much more entropy than solid and liquid. So if there are gases involved, we don't even look at anything else.
And so the entropy value is negative. Why? Is it because there's less? I just don't.
We say the entropy of this here reactant. Total entropy of the reactant. We can actually easily calculate it. We can ask our phone and find the entropy for both of them without any problem very quickly. Not a problem. But suppose we do that and we say the entropy of this is A. This is A of the reactants.
Okay.
Or R for the reactant. Entropy of the product is P. Which one is bigger than which one?
Products are bigger.
Products are bigger. P is bigger than R. So because of this reaction happened, what happened to the entropy? Increased or decreased?
It would increase.
It would increase, right?
It's increased. So what should we do over here?
So it should be positive?
It should be positive, not negative.
Okay, yeah. All right, that makes more sense. And then for 2, it should be negative.
Let's look at that again. Now this
because we're going from full 4 moles.
So that's negative.
Yeah.
Fine. Number 2 here, this entropy is more, it decreased. Therefore, this should be negative.
All right, yeah, that makes sense.
Good. Now, we already saw that. We already calculated it right here. We calculated this entropy minus 198. This is what we came up with, 199, 198. Okay, so minus, the entropy decreased. All right. I don't want it over here. No. Equilibrium. What does that mean? And there is no heat involved here. Let's get rid of this heat business. Get rid of the heat here in your, there is no heat involved. Equilibrium, what does that mean? That means this reaction is a reversible reaction, is going back and forth all the time. What is the delta H value and what is the delta S value? When something is at equilibrium, when a reaction is at equilibrium, the enthalpy value is 0 and the entropy value is also 0, equilibrium. It's not changing. Equilibrium means there are so many moles of products are there and so many moles of reactants are there. There is no net change. Therefore, the value are 0, 0. Zero, you can write your units here. I'm not going to write units because that just takes a little bit longer time. All right. Solvation, meaning to dissolve. It's not a chemical reaction, it's a physical process. But physical processes also have change of entropy and enthalpy, of course. So now, what would we say? Heat is a reactant here. So what is the delta H value, positive or negative? You're putting heat into the system. So delta H value is?
Positive.
Positive. And and then we are talking about which one has more disorder, a solid or a dissolved mixture, where the molecules are more freer to move,
Dissolved.
in the solid or in the dissolved mixture?
In the dissolved, right?
In the dissolved mixture, therefore, entropy has increased because of this process. Heat is a reactant, therefore is positive.
Professor, you skipped one.
Oh, we are doing number, oh,
Yeah,
this one. Okay.
The other one after
Okay.
0.
All right. We have a solid and we have aqueous mixture, and the solid got converted into ions, and we have water liquid over here, and we have 2 moles of gas produced. Is there any comparison? There are no moles of gas as a reactant. There are 2 moles of gas as a product. Gas is by far the greatest amount of entropy. So if we say 2 moles of gas as a product, then that just means 0 moles of gas as a reactant. So that means great amount of energy increase, entropy increase. So this is going to be positive here.
Positive.
Yeah, forget again. Positive. And this is heat is a reactant or a product. It's a product, therefore delta H value is going to be negative. Heat is going out of the system. Okay, this heat is a reactant, so that's positive. Delta H value is positive. And then we have no moles of gas over here and 2 moles of gas over here. Well, you know the answer. What is the answer?
Should be positive.
Positive.
Positive. So we are comparing the moles of gas for the reactant and for the product. If that doesn't work, if there are no moles of gas involved, and then we go to other things. But the first thing we do is we compare the moles of gas of the reactant and the products. So here are 3 moles of gas as the product, no moles of gas as a reactant. Hey, that means it's positive. And heat is a reactant, and so this is going to be positive also. Okay. I just talked about this with you guys. So in the 2 minutes that we have, I want you to read these 2 paragraphs here. Entropy changes and that. I just talked about it. And I wrote it down better than I talked about. So read that, and that's you should understand. Then we are going to take a 30-minute break. We will meet again at 1:50. So just read this here. It's good to talk about tax relief these days. I just got my check. And this time there was no sign on signature of the president on the check.
There wasn't
I
gonna,
noticed
he
that.
wasn't gonna sign
Last
it.
time there was, this time there was none. I wonder what that means.
That means that you're gonna have to pay it back because he didn't really approve it.
So I can go eat.
So if you and I get a tax relief of $1,200, that means something to us. A billionaire get a tax relief of $1,200, that billionaire can care less about $1,200. That's how we see that if the more heat is released by the system in the surrounding, depends upon the temperature of the surrounding, that how much entropy. If the temperature of the surrounding is very high, more heat release in the surrounding doesn't mean much. But if the temperature of the surrounding is very low, if the entropy of the surrounding is low, then that heat released mean more. Therefore, entropy is inversely proportional to temperature. Okay. All right. I'll see you in half an hour.
Professor, quick question.
Yes.
In that case, shouldn't it be for delta H and delta S, shouldn't they be inverse? So if heat goes into the surrounding, then delta S should be positive. But if heat is taken up by the, I don't know how to word this.
If the heat goes into the surrounding, that affects the entropy. If it goes into the surrounding, that also affects enthalpy. So that's number one. Number two, because the heat is going into the surrounding, then the enthalpy is going to be negative. That's what you are saying. This is correct.
But then doesn't it say?
So that then we say for the entropy, if the heat goes into the surrounding, it is inversely proportional.
Yeah. So then wouldn't it be if?
So that's why you cannot say what you were saying.
Okay.
Because it's not directly proportional. What is not directly proportional? The heat going into the surrounding and the entropy change. They are inversely proportional.
So wouldn't it be if the surrounding loses heat and then therefore delta S surrounding is less than 0, so wouldn't delta S be negative?
If heat goes into the system from the surrounding, everything else being the same, that would increase the entropy of the system. And we can see that you're right, that we can see on a cold day, heat goes out of our body into the surrounding. We want to decrease that, so we put on a sweater. On a hot day, or when the temperature increases, I will take off this sweater because now I don't want to keep the heat inside. I want to let it out. So that's one way to look at it. It does not address what you were saying, but it's a little more complicated.
Yeah,
I'm inversely proportional. That's why. If it would be directly proportional, we could say yes, but inversely proportional. So we have to look at each one of the cases specifically. Also, usually there are also other changes happening. So everything being the same, we might be able to compare something easily. But when everything being the same is at equilibrium, then these are going to be equal. See the 0, 0. So you're right. Everything being the same, it would be delta H value will be 0 and delta S value will be 0 too. But then after that, I don't know how to answer your question. I think I will have to deal with it every system separately.
Okay.
Professor,
All right. Good questions.
I don't have a
You
question.
soon.
I
Oh,
just have a
go on.
question. I have an appointment for MRI in Fremont. I have to be there before 3, so I won't make it the rest of the class, but I'll rewatch the lecture later.
Yeah, good. Okay, so we will make sure that we
Yeah, I'll rewatch to take the rest of the notes.
okay. All right. Bye.
See you later. Bye.